2 минуты на вопросы. Good afternoon, dear colleagues. I'm happy that I have the opportunity to speak in front of such professional audience and speak about the problems of creation of dense point cloud that Viktor Nikolaevich referred to here. We all know that virtually all software, photogrammetric stations, all of them have a module, almost all of them have a module to build such dense point cloud for all images. And Photomod is not an exclusion here. On one hand, it might seem that this process works very well in all cases. I think it's not completely true, and the market is not standing still here, and I think that these methods will get better and better with time. I'd like to speak today to you about algorithms of building such dense point clouds, and first of all about the famous semi-global matching that was offered as early as by Hirsch Müller in 2005. On this slide you can see the so-called main basic idea of creating dense point cloud, which is about the following. At the first stage, the stereo pair of images, and this method of semi-global matching is based on the processing of separate stereo pairs, which originally were to be transformed or rectified along the basic lines or epipolar lines. I will use Russian terms here anyway. So, based on the elements of external orientation, this stereo pair is transformed, and as a result we get the following situation. Each pixel on the left image is placed on the relevant line on the basic line of the right image, which helps us in better matching the points. And our main task is to find matching of each pixel on the left image and find its matching pixel on the right image. On the right image, it is located along this basis line. It's just that we don't know where exactly on this line it can be found. That is why each pixel of the left image is compared to the pixels on the right image, and the difference is recorded then, which we call the value of this matching, which can be shown in different brightness of different pixels, and then recorded into this column of this spatial structure. That's what we do for all pixels. The second pixel is again compared with all the pixels with all the changes of the latitudinal parallaxes on the right images, and we get this structure of values of matching. Then we analyze these values for identification of minimal values. Two images on left and right images would be more likely to have the minimum values, and within this cube we see the value for the first pixel. It is the minimal is here. For instance, for that pixel, parallax is equal 1, 2, 3, 4 is equal to 4. For the next pixel, the minimal value is located here. This way, if we do this simple elementary operation for all pixels of the left images, comparing them to the pixels on the right image, we get for each pixel its matching lateral parallax. Knowing the lateral parallax, we can get a matching point and get three coordinates x, y, z within the system of coordinates of an object. And it seems to be a ready-to-use point cloud with a 1 pixel resolution or step. But this is a simple algorithm which is just the first approximation for acquisition of this point cloud. At the next stage, we have to add values depending on the changes of the lateral parallaxes from pixel to pixel. We analyze these changes based on 8 different directions, and this is what semi-global matching of these points is all about. We analyze all pixels. For each pixel we analyze absolutely all neighboring pixels. It takes a while, and that's why they invented semi-global matching method, which is based on the analysis of only pixels along one line. And there are 8 lines or directions usually. There could be more, of course, but people mostly use 8 directions, just like it is shown on this slide. As a result, we get the sum of all, yes, before I forget, and the bigger is the difference of lateral parallaxes with the neighboring pixels. The biggest is the fine, the biggest is the addition to the source value of the matching. And based on this formula, we get the sum of values for each pixel. We analyze it for identification of minimal values, and we get it as a final result. And we get the famous point cloud in form of points with the famous XYZ coordinates, and the brightness which we source from the source image. As a result, we get a texturized image in form, again, I repeat, of the randomized point cloud. This approach, of course, has its own advantages, among which would be good results of matching, even on the lowly texturized parts. And when we have different contours, high resolution, and good speed indicators, because this method helps us organize parallel computation, and the speed of computation in some cases can be as high as real-time computation. But there are also inherent problems to this method, the SGM method, shall we call it this, semi-global matching. It's hard to do the matching of points for all images. Here, the main basis for matching is the stereo pair. That is why we have to transform this stereo pair each time, and there could be potentially a lot of stereo pairs. And if we take aerial imagery acquired from UAVs, the overlaps are multiple there, and each time we have to transform them. We can transform each image a dozen times. Sometimes it could be so difficult and so complicated. That is why naturally it slows down the process considerably to build dense point cloud, and we need to somehow combat it. Most importantly is that we're not using to full extent all photogrammetric connections in this regard. That is why it was suggested 2 years ago to use a new modified method of this semi-global matching in object space. And I must say that this modification, so it happened, was done simultaneously by 2 groups of scientists in Waldenburg, Professor Luhmann, and in Migaik. It was done independently from each other. The main idea behind this method is in the following. The whole object first is split into spatial structure, voxel structure, with the size equal to the size of the area. Each size of the voxel, delta x, delta y, and delta z, is based on the accuracy that you want to get the digital terrain model. Or, what is more logical, it can be equal to the image resolution or ground sampling distance. Then, sequentially, for each of this voxel, we calculate the position of this point on all the images where we can find this image, or we can find this point. And we calculate the values of matching, which can be calculated similarly to a classical method SGM, as a difference between brightnesses of neighboring pixels. and we calculate these differences in brightness for all combinations of all the images where this point can be seen. And we take minimal values and put it into the voxel structure. As a criterion for evaluation of this matching, we can use not only differences but also the correlation coefficient, which naturally can increase the level of matching. The matching will be much greater, especially in the dead zones. Later on, we analyze not the matching, not the neighboring lateral parallaxes, but rather the heights of neighboring voxels. And based on the same principle, just like in the classical SGM method, we increase their value. And as a result, we acquire, after analyzing these voxels on z-axis, depending on the differences in heights of neighboring voxels, we add the value. As a result, we analyze the value which is calculated as a sum of all the values calculated based on these 8 directions. But just like as shown on this slide, for this particular pixel we analyzed voxels on 8 directions, and as a result we add it to the value. And the result, we get again the minimal value for each voxel, which means that here it's more likely that we have matching of these points in all the images where this point can be seen.
And finally we get a digital surface model with the density that we selected, but looking as a regular structure. At the base it's delta x, delta y, and at each node we have the z or z height. If you add density or the brightness of a true image, we'll get a true ortho photo. A month ago, Professor Luhmann at a Photogrammetry week presented the results of a pilot calculations. Our team force at MIGAI has done it with very good results. If you want to find out more details, you need to follow this link. That's from the Photogrammetry week's findings. I will share with you just one example of this pilot research. So a test area was selected for a downtown area of Munich where the elevation difference can reach 50 meters. DMC2 was used to make aerial photography. GSD 10 centimeters. Overlap across and along is 80%. On the ground, we selected voxel of 10 centimeters. About 12 million points were generated. This is the initial point cloud, and this is the derived surface model as TIN. This is an example of the same area of interest. No manual interference was made, so it's a purely automatic product. And the most fun part of this project is the quantifiable results of the project. The green shows the divergences for 12 million points within the range of 30 centimeters. That's 3 voxels. Most of the errors up to a pixel size were 75%. 2 pixels or 2 voxels is 84%. So the results are pretty good. Quite decent, I should say. Of course, we shouldn't say that this is a panacea, a cure against all problems. I'm sure there will be further modifications. Again, this is orthophoto as a side product of point cloud generation. As you can see, again, the level of detail is quite decent. This is the wall of the building in the octagonal projection. So what are the cons and pros of this method? All the benefits and advantages of SGM remain. A definite plus of this method is, of course, you don't have to make transformation. We use initial images with sub-pixel accuracy. You can work with all the images as opposed to working with stereo pairs. I, for one, believe that this is another advantage. I talked about orthophoto, and what Professor Luhmann obtained confirms high efficiency of this approach. Looking ahead, in order to receive information faster, it makes sense, and it will be easy, to use the existing 3D models, because we will immediately obtain the first approximation of the surface in considerable terms. Then we can use the same voxel pyramid, but in order to increase accuracy of point cloud during the final stage, I think we need to use a method suggested by Professor Grun, who I hoped to see today. It's he has his grandson or great-grandson on the way, so he couldn't come. As far as I know, this method didn't take off very quickly, but this is the essence of this method. This is a digital surface model that we generated using SGM, and for each orthophoto pixel we can record this kind of equation that links orthophoto pixel brightness a certain point on the ground and the brightnesses of this point. X and Y coordinates are calculated using the known collinearity formulas. I think that this is where researchers are going to look for in the future. Well, I guess that's all from me. Thank you very much. Спасибо, Александр. Мы можем 2-3 вопроса выслушать. I have one question, Alexander. I may have missed it. What did you compare against with that slide? What was the reference? I don't know how to call it. Yes, I didn't mention the test area in Munich So for that test area, a point cloud surface model was generated based on images from 10 sources. You know, all of them. Everything but the kitchen sink. And finally we arrived at the average from the 10. And it was a kind of reference that we compared against. Alexander, if we imagine that we use SMG in order to figure out flight angles, roll, pitch, yaw, you don't need them. They have no influence. That's right, they have no influence anymore. You need to perform area triangulation. In terms of technology, nothing changes. Only your approach to processing changes. So you don't need triangulation. Of course you need it. Without triangulation, it's a must. For each image, we need to have external orientation elements. So photo triangulation is a must. Alexander, a while ago we did a research and there was a question about the optimal number of images for SGM. When you have a lot of overlaps, for example, are there any recommendations as to the best number of images? We decided that it should be 21 images to give you best accuracy. What can you say? I don't know. I've never heard about such studies, but you just have to use your common sense to figure out overlaps. First of all, we are driven by the amount of information we have. If you create a 3D model of a city, of course, you will need to use oblique images because facades need to be represented correctly. In terms of geometry of coordinates, you said that you arrived at 21 images. That could be, but I would say there could be fewer images necessary. But for complete information, 21 is better than 10, for sure. But if your processing algorithm takes into account geometry of each point, including the resection point, I guess 10 should be enough. Mr. Zaichko, Roscosmos. I have a slightly different question. I am wondering about your activity at MIGAIC on the certification avenue. Actually, my question also goes to Mr. Amatio Pilet. We at Russia today try to make remote sensing data of legal validity, so that it is found as having legal validity. I was wondering how far did you go at MIGAIC, and what about you in Israel? Where do you stand on this about legal validity of remote sensing data? be it from UAVs or space. How do you treat? I'll go first. I think legally, this document will become legally valid when the certain legislation is in place. At this point, there is no legislation in place. Therefore, an authority that claims that this document is of legal validity, it has to be very professional or credible at least. If you issued a document and say, this remote sensing document or product meets certain requirements, and there should be no questions asked, no doubts, even from lawyers, because your reputation will be at stake at this point. Later, when laws are passed, and based on experiences of the future, we can talk about legal validity. Alexander, we have the law already in place in the Forest Code. What next? So the Forest Code obliges us to provide space images as a proof, as evidence of illegal logging. So what do we do next? Who's going to certify this data? We are willing to assume responsibility and validate the image characteristics. No problem. Validate the characteristics that are there.
In Israel, and it has nothing to do with the survey. In Israel, everything, if you want to certify, should go through a court. Only a judge who knows nothing about Roscosmos or about Migaik or about Valery Zechko personally, doesn't matter. You have to go to court in order to validate. If you have a stamp or whatever from court judge, then it's okay. That's the only way. But even if the survey in Israel is the only one who is allowed to, I think, give certification for cameras and for others. If somebody would like to stand against it, they can go to a court. Well, there is, oh, sorry. Okay,
Michael,
thank you. There's
yeah,
one, okay.
Michael
You're the
Yunan.
last.
Yes, okay. The SMG, what are the accuracies of the X, Y, and Z? Has this been checked? The accuracy?
Of course, we have accuracy data. In my presentation, I said that accuracy is estimated at 1 pixel size. So it's 75% accuracy for 1 pixel on the ground. For 3 axes, X, Y, Z. And for Z, you consider the same pixel. The pixel size is the same for all coordinates. It's 10 centimeter GSD and 10 centimeter delta X, delta Y, and delta Z. That's what we call voxel size.